Hello, the internet, and welcome to Open Source Directions, hosted by Quansight, the webinar that brings you all of the news about the future of your favorite open source projects. My name is Anthony Skopatz, and your host for Open Source Directions, and co-hosting with me today is Carol.
Hi, I'm Carol Willing, and I'm an active member of the Jupyter and Python communities, and I'm very happy to have an opportunity to chat today about UMAP with Leland. And Leland, maybe tell us where you're from.
I'm Leland McInnes. I'm from the Tufts Institute for Mathematics and Computing. I'm a researcher there. I'm really mostly a mathematician, but I apparently accidentally got involved in open source software development. So now I'm stuck maintaining it.
Accidentally, yes. Well, we're really excited to have you here today, Leland. And before we get into UMAP and all the fun UMAP discussion, we like to do a personalization section. So first, we're going to chat about sort of our favorite new open source projects. And so Leland or Carol, Leland, do you have one that you'd like to share? Or is there anything
yeah, so one that came across recently that I quite like is called Stumpy, which is for doing matrix profiling of time series. It's a little bit of a niche library, but it's a very novel approach to time series analysis, and I really like it. It's very clean, well written, and I'm looking forward to getting to explore more with that.
Very cool. Sounds interesting. I had a library. It's called I don't know if it's GUIX or GUIX, but basically it's another early project that's taking a look at how to make Jupyter notebooks reproducible, and I think Brandon's going to drop a link in it, but they have a new blog post out, and I'm looking forward to testing it out and seeing how reproducible things are. But
yeah, that's that's excellent. For my share today, I'd like to highlight Sphinx Math Dollar, which is this new project by Aaron Muir, also of Quansight here, which solves one of my biggest long-standing gripes with Sphinx, which is that you can't enter math mode like you do in LaTeX with just dollar signs. So with that project, you can. It's amazing. It was only started like last week, so it doesn't have a huge, user base yet, but you know, this is a new open source project, so go with and use. It
works really well too.
And it works, yeah, which is awesome. So with that, thanks everybody. Now we're going to talk about UMAP, so or the Uniform Manifold Approximation and Projection, or UMAP. It's a dimension reduction technique that can be used for visualization, similarly to t-SNE, although it does a lot of other stuff and has a wonderful mathematical basis behind it. The project that implements UMAP is up on GitHub, and the repo currently has about 3.3 thousand stars right now. And there's a really good SciPy talk we'll link to from SciPy 2018 that Leland also gave, that kind of gives a really nice overview of the talk. But we're just going to ask you a few questions, Leland, and have a sort of a conversational introduction to the project here.
Yeah. So, Leland, maybe you could tell us a little bit about why the project was started and what need it fills in this space.
So I actually started the project for something very different. Originally, I wanted to solve the problem of combining different metric spaces or data from different metric spaces all into one space. So ideally, that would allow you to do things like take a pandas data frame with lots of different types of data and just put it all into numeric space in a nice way. And I developed some theory for how to do that, got started working on that, and then discovered that the things I needed to do required a dimension reduction algorithm, and that sort of has ended up taking up all the time, as it turned out. So it was not the most direct approach to getting there, but this is how it's turned out, and I'm still working on the applying UMAP to data frames. most of the way there, but not there yet. Instead, it's the project kind of expanded in its own directions.
Yeah, that's really interesting how these things get started and develop. So are there alternative projects to UMAP out there?
There are lots. UMAP's really just about dimension reduction, as you spoke about. So reducing dimensions from very high dimensional data down to something you can ideally visualize, or maybe something you can cluster. But there's a lot of methods to do that. Scikit-learn has a whole bunch of them in its sklearn.manifold section. So there's a whole bunch there. And then there are a lot of implementations of t-SNE, which is probably the most popular method out there at the moment for doing this sort of thing. So there's a wide variety of, I guess, similar tools. UMAP is its own unique take on the algorithm for how to do this.
That's interesting. So given that you have a unique take, what technology is UMAP built upon?
So in terms of building out Python technology to implement the mathematical ideas I had, it's all founded on the usual PyData stack, NumPy, SciPy, and these sorts of things. But probably the thing that has made the most difference to UMAP is Number, which is a just-in-time compiler for Python down to LLVM. And that was really critical for me because it let me, as a mathematician, just write Python code and still have it run really, really fast. So I've made huge amounts of use of Number, really, to make this project workable at all. I think if you turn Number JIT compiling off on the UMAP repo, you'll find that it essentially won't actually even run. It'll just take forever to do anything. So
yeah, Number is great. Totally great.
Yeah, definitely worth more discussion as well going forward. So who started the UMAP project? Was it you, or was it a team at your institute?
So it was primarily me. I have a bunch of colleagues at the Institute, and we work on a variety of different problems. We sort of drop in on each other's work every now and then. So I certainly got a lot of input during the process of getting it going. But in the end, it was mostly started by me, and it started to draw in contributors from all over now, which has been really, really interesting to see and see different perspectives on things.
I mean, it's kind of interesting because it sounds like you're the primary maintainer. What are you doing to sort of build the community?
Well, I'm doing my best to try and make it a welcoming place for people. We have a code of conduct. We're trying to hold to that and try and make it welcoming for new people. And really, I think the goal is just to try and, if anyone wants to contribute anything, we're more than happy to see them come on board, especially documentation. I think a lot of the questions that I can see showing up in the chat there are about, issues about how it works and things like that. And more documentation on that would obviously be good. And to be honest, I'm really bad at writing that because it all makes sense to me. So I need somebody coming at it with a different perspective. And furthermore, one last thing, if there's anybody from any underrepresented groups that would really like to join on this project, I'd actually be happy to mentor anyone if they want to come on.
Fantastic.
And do that.
Yeah, excellent. So where are the users of UMAP typically coming from? Sort of what communities, what disciplines, what are the use cases that they're targeting this for?
The use cases have been surprisingly varied and pretty interesting for me to learn a whole lot of new subjects. There's a whole lot of people from biology that I know very little about and have had to try and learn a lot about, single cell biology particularly. But there's also seen a lot of use in materials science. It shows up a lot in machine learning work. I've seen it used for astronomy and astrophysics.
Right.
There's even computational social science. I've seen actually some really interesting uses of it where it's been quite productive. So it's been a pretty diverse range of fields, and I've been trying to learn as much as I can about the fields to help people use it better in those fields, but it's been an interesting journey on that front.
That is challenging, and that's probably, you know, like as you mentioned before when we were talking about community, you know, having documentation always kind of helps, and it's a great place for people to start. We typically ask each maintainer like what they're doing for diversity and inclusion within the project. Is there anything else beyond what we just talked about?
I think I covered most of it. We don't have any formal diversity and inclusion efforts at this time. To be honest, the project's sort of grown rapidly, and
makes sense.
I'm really not familiar with these approaches. So if somebody would like to come and help the project with diversity and inclusion efforts, I'd really welcome that. That's not something I have expertise in. So it'd be really great if somebody wanted to help with that, because it is something I believe the project should do.
And I know you and I had talked the other day about how you've put in the fundamental first steps for really having a successful open source project. So that's great, and I commend you for doing that. So now I think we get to some of the fun stuff. Isn't that right, Anthony?
Yeah, that's right. So now we get to see a demo and a walkthrough here. So I believe you already have some things you want to share, Leland. If you want to go ahead and share your
yeah, I'll give this a go and see if I can get this up.
Yeah.
All right. So before I go through this, I just want to point out that all of this that I'm about to walk through just here is in the documentation on UMAP Online. So if I scroll through everything kind of quickly and you don't really get to see it, don't worry, you can go and look it all up online. You can also get the notebooks online. I'll post a link to where you can find those. So first of all, just a quick introduction to what UMAP is, because while I think some people attending this are familiar with it and want to know more, I presume some people don't really know that much about it yet. So the goal here is to take high dimensional data and reduce it to something that's lower dimensional and easier to represent. So for the demo purposes, we're going to look at first the iris dataset, which is a classic dataset of measurements of iris flowers. And it's four-dimensional because you have measurements of sepal length, sepal width, petal length, and petal width. So four-dimensional data, you can't really just plot it immediately. You can do a pairs plot where you look at each dimension against each other. And you can see for the iris data set here, where we've colored it by the class of iris flower that it was from, you can get a reasonable idea with the pairs plot, but it's a lot of things, a lot of little plots to be staring at and try and understand. So the goal would be to try and find a presentation of that data that captures most of the structure in the data, but is just one plot. So to use UMAP to do that, we'd just import the library. And then UMAP follows the scikit-learn APIs. So the goal there is that you instantiate an object with parameters, and then you fit it to data, and then apply either a transform or a prediction from there. So we're going to create a reducer object by just instantiating UMAP. And then we're going to create that low-dimensional embedding by fitting and then transforming the iris data set. So we do that, and we get out an embedding, which is 150 data points, which is however many data points iris has, but it's only 2 dimensions. And we can plot that and see that this looks a lot like the views we sort of imagine we got from that pairs plot, but it's now just a single plot in 2 dimensions. But let's scale up a little bit and look at a different data set, the digits data set. So this is again from sklearn. You can just load it straight away. And it's 8 by 8 pixel images of handwritten digits. So here's a whole bunch of those images. And when you unravel those 8 by 8 pixel grayscale images, you get 64 dimensional vectors. So now we're a lot higher than 4 dimensions, and it's a lot harder to understand what's going on. So if we tried to do a pairs plot, we get something like this. In practice, there'd actually be 64 by 64 in this grid, and it would be even harder to look at. This is just a sampling, and you can see it's very hard to actually understand what is going on with this data from something like a pairs plot. But we can take UMAP, again, initiate it, the object, and then fit it to the data. And now when we plot the two-dimensional representation we get something like this. So here we've colored each of the points by the actual numeric value of the digit it was supposed to represent. And you can see that it's captured a lot of the structure in that data set in a way that presents it to you so you can see what's going on with the data pretty clearly, even though it's originally 64-dimensional data. Now, there are some quirky bits and pieces. There are down here at the bottom, these ones that are somehow separated from all the rest. And then there are these nines here that are, again, separated from the rest of the clump. We can actually go through and build a little bokeh app to allow us to hover over the digits and see what actual image is associated with the individual points. And you look, if we go down to the bottom here, these are all the ones that have feet on them. Whereas most of the ones up here are just the single lines. So it does actually make sense that it separated them out. These are kind of distinct looking things. And similarly, the nines that got separated out are the sort of rather more stick-like nines, which are oddly enough related to the sevens with a cross in them. That makes a lot of sense. Whereas the nines down here are the very rounded nines that look, again, very distinct. So even though we didn't separate out the actual digit classes absolutely perfectly and clump them together, we're seeing that it actually did the sensible thing of transforming the data in a way that respects what the data actually looks like. So this is a meaningful representation.
That's amazing. This is a great visualization and walkthrough. Right. So the other thing that we could look at, I'll go through this one a little more quickly when I get there, is issues of performance. So one of the questions that gets raised is how fast can these algorithms run? And for this purpose, I'm just going to look at t-SNE from sklearn and then the multi-core t-SNE package, plus a bunch of other algorithms from sklearn for doing dimension reduction. Sure. So what you're probably most interested in is how this is going to scale with data set size. So we can run all the algorithms for data sets of varying size and see how long it takes to run. And the short answer is that there are a couple that just take a really long time. The sklearn t-SNE is a bit slower. They have done significant work to speed that up, and I think in upcoming releases of sklearn, it's going to be a lot faster than this. Multidimensional scaling, you can see the quadratic looking curve on that is only going to get worse. You really can't do very large data sets with it at all, whereas there's this group that's generally faster. But if we go through and zoom in on just those sets and scale out to ever larger data sets, you can see that UMAP is among the very fastest. It's not as fast as principal component analysis, but principal component analysis is really just a linear projection of your data. So it doesn't show you anywhere near as much of the interesting structure that you get. Whereas UMAP can do these more complicated nonlinear transforms similar to t-SNE, but it's faster than almost all of the t-SNE packages out there. So if you're just looking at raw speed, UMAP is definitely one of the options. And this is a single core version of UMAP, right? It's not a multi-core version that you're comparing.
Yeah, this is single threaded because I wrote the easiest possible thing I could do. I used number to make it go fast, but but making it multi-core is multi-core is definitely a challenge, and hopefully we'll get a chance to discuss that a little later. So that's probably it for the walkthrough for now, unless there's more you'd like to see. How are we doing for time?
We're totally fine on time if there's anything else that you'd like to show us. So if you have something in your back pocket.
Okay, yeah. So just to add one more thing to the list, let's have a look at doing clustering.
Excellent.
So this is a different data set again, but it's slightly closer to sort of more real world data set, although it's not really real world. It's MNIST digits this time. So this time it's 28 by 28 pixel images of handwritten digits. And with that data, you're looking at 784 dimensions. So now it's really quite high dimensional and harder to work with. So this is what a UMAP projection of that 70,000 points in 784 dimensional space looks like, again, colored by the actual numeric value of the digit it was supposed to represent. And you can see UMAP's done a pretty good job of separating out all the digit classes in a sensible way. So this is good, but what if we actually want to do clustering on MNIST digits? How does that work out? Well, to start with, we could look at what we would get if we just did k-means clustering in the original 784 dimensional space. So we're going to work on just the full 784 dimensional data, and we can color the embedding, the UMAP embedding we just did up above, by the cluster label that k-means assigned. And you can see that k-means has kind of chopped everything up in all sorts of weird ways, especially when you recall that the embedding did such a good job when considered by the actual digit class. So k-means isn't really doing a great job. That's not that surprising. K-means is a fairly basic clustering algorithm, and it's working in a very high dimensional space. So we can even look at the measures of how well it's doing. I won't go into the details of exactly how this is measuring things, but it's essentially how well do your cluster labels match the actual label values in the data, because we happen to know that for this particular time. This gives values between 0 and 1, 1 meaning you did it perfectly, and 0 meaning your labels, cluster labels, are essentially just random. And as you can see, k-means is getting 0.36 by one measure, 0.49 by another. It's not that great. It's really not respecting the labels very well. Now, we could do HDB scan, which is a more advanced density-based clustering algorithm, and apply that in the high dimensional space. Or in practice, actually, we're going to PCA it down to 50 dimensions so that it's more tractable for HDB scan to work with. And what we get out is this. So here the gray denotes points that HDB scan refused to cluster. It just called them noise points. And you can see it's most of the data is not clustered, but it has clustered a bunch of points, and it seems to be doing an okay job of that. If we look at the scores, though, we see that, in fact, HDB scan did a terrible job compared to k-means. That's actually because it declared most of the data noise. If we generate the same scores on the data that HDB scan actually was willing to cluster, it's almost perfect. So this is not so bad. This is the way HDB scan's designed. It's supposed to get things right where it can get it right, and where it doesn't know, just punt and say, I don't know, and that's fine. But what if we actually want to cluster the data? Well, we can tweak the UMAP parameters a little bit, designed for clustering. The documentation has details on how to do that, and get out a more sort of tightly clustered embedding designed specifically for running clustering on. And now if we run HDB scan on that, we find that the cluster labels, oddly enough, line up almost perfectly with the actual digit classes. And when we run our scoring on this, we get sort of in the order of like 90% sort of accuracy. So by applying UMAP first and then doing the clustering algorithm, this gives density-based algorithms a lot more traction to work with in the lower dimensional space. And so now we can get really, really good clusterings of very high dimensional data by using UMAP as this interim step to bring it down to something that a density-based clustering algorithm can get traction with. So this is how you can use UMAP for something other than just visualization alone. You could reduce this to 10 dimensions with UMAP and cluster in 10 dimensions, give yourself a little more freedom rather than having to do 2 dimensions.
So it's a tool that then helps improve some of the other tools in your data science toolbox. Is that like it's specifically the clustering?
Yeah, clustering is one option, but there are other things you could do further along in the pipeline as well.
Sure.
So yeah.
Great. Well, thank you so much for that walkthrough. Do you have any other questions, Carol?
No, it's pretty cool. I mean, to go from those two-dimensional plots where it looked like just a color map and to something where you could actually kind of see the distinct areas was really cool. So it's pretty powerful that way.
Yeah, very much so. So it is now time for our roadmap discussion. So this is where we'll be talking about where the UMAP project is going and some of the the future looking parts of UMAP and these for our viewers at home, these are places where UMAP could really benefit either from contribution in code or in funding if you have deeper pockets and would like to fund UMAP to move in a particular direction. These are all places where you can dive in and contribute in any way possible. So I know that you have a few roadmap items that we want to discuss. So Leland, what's the first one here?
So I'm actually going to start with some of the stuff that's in the upcoming release. We are working hard to get the 0.4 version of UMAP released, and it's got a bunch of new features. A number of them are still being tweaked and polished, so it's not quite there yet. So hopefully we'll get the release out, and all of this that I'm going to show is really documentation of the upcoming features. They're not necessarily all absolutely finished yet. So let's see if I can quickly find that. So one of the first things that's coming in the 0.4 release is a little plotting extension library. So what this is going to do is make plotting UMAP a lot easier. So all you're going to do is import UMAP plot, and then you can do UMAP.plot points and hand it just a UMAP model, and it'll do the rest. It does all the things like deciding the right point size to use, watermarking with the actual UMAP parameters that you ran with, and all those sorts of things. It also makes it a lot easier to add labels or color by values. There are just simple keyword arguments to make that really straightforward. Color theming and all that sort of thing is easy. It's not a complete plotting library. If you really want to do advanced or interesting plots, it's not going to do that. This is more designed for just make it really easy to get to a plot in just a line of code that does most of what you want. Better yet, if you have large data, it'll automatically use data shader to do your plotting for you to get rid of all the overplotting concerns that happen. So again, it's trying to do the smart thing and look at your data, see what it looks like, and do the right kind of plotting. So data shader is automatic. You don't have to do anything different. You map plot points, and if you have enough points, it'll say, you should use data shader to do this. Interactive plotting is another one that comes up a lot, where you want to be able to hover over your data or zoom in on your data. I see people doing this all the time. So there's just a umap.plot.interactive that'll make that straightforward to do. And then there's a bunch of diagnostic plotting that this is really just the start. This is one of the areas where I feel like it'd be a good place for people to contribute. One is that there's a underlying connectivity graph in UMAP, so we can actually plot those graphs for you to have a look at them. And then more specific, just diagnosis plots where you can color by the PCA embedding, color by vector quantization, color by an estimation of the local dimension of the data at that point, or color by the neighborhood accuracy. There are a lot more things along these sorts of lines of diagnostic plots that maybe could be done. If people have ideas of things that they do, this would be a great place to try and add some things.
Go ahead, Anthony. I was going to say.
Oh, yeah, I was just going to say, that seems like a great place for people to jump in. So.
Yeah, I would love to see somebody use something like IPy volume with some of those structure plots. Might be really cool, because then you could manipulate them too. I don't know.
Oh, absolutely. Yeah. 3D plotting would be a great thing to have as well. I don't have a lot of experience with that. So if somebody who does have more experience with, say, IPy volume would like to come and add that to the plotting library, that would be a great place to jump in. So in terms of new features, some of the other things that we've got coming up are an inverse transform. This is still pretty experimental, so I'm going to warn you, it might not necessarily work perfectly on your data, but the principle is there. This was actually great work by one of the early contributors, Joseph Courtney, who came in and after some discussions went and just added all this functionality himself. So I was very happy to see this come in and work. And the goal here is that if you have a UMAP plot in low dimensions, you can pick out points in the low dimensional space and then transform that back and generate the equivalent point in the high dimensional space. So here we have MNIST digits, and we're taking a grid sampling of points in that embedded space and generating the digit that would have generated that point in the embedding. So this is a great feature for people who want to understand a little bit more about what is causing the plot UMAP results to come out the way it is. You can sample some points and project them back up to high dimensions and find out what it is about those points that's making them land there. So that's pretty really powerful new feature.
Yeah.
Really how expensive is that operation, just out of curiosity?
Somewhere between reasonably and very.
Yeah.
It's not cheap. It does definitely take some compute to do that. It's solving an optimization problem to do it, and that's really some compute. It's not a PCA style inverse transform where it's just doing a matrix multiply. It has to do some.
Can you swap out the optimizers for that step, or is it a single like gradient descent or what?
It's all the custom internal optimizers that UMAP already uses. So on the upside, it's reusing a lot of the optimizers that UMAP wrote originally for doing the low dimensional embedding. We're just flipping it around and using that to do the inverse. We also have UMAP for sparse data now. So if you have sparse matrix data, you don't have to have it filled out as a giant array in memory. You can use the SciPy sparse format of sparse matrices that is a lot less memory intensive, and UMAP will work just fine on that and do low dimensional embeddings of sparse matrices. And now it also supports transforming data into those low dimensional embeddings from yet more sparse data. So an example of where this sort of thing might be useful is text analytics. So in text analytics, often you will do something like a TF-IDF matrix of your giant corpus of text, and that's a really high dimensional, really sparse matrix, and UMAP can now just work directly on that and still have the transform work directly on that. So this is UMAP with TF-IDF of the 20 newsgroups data set, and it works just fine and pretty fast. So we've really upgraded the sparse data handling to be a little more powerful. A couple other things that are in the upcoming list.
Question there. Do you have you thought about working with PyData sparse as well, or is that on the roadmap, or is that something where contributions would be welcome?
That is a place where contributions would be very helpful. I have not worked with the PyData sparse library at all. I have a reasonable amount of familiarity with the internals of the SciPy sparse matrix formats, which is really what enabled this to happen, because you have to dig into the internals to make it play nicely with number. So somebody with familiarities on the internals of the sparse library, that would be a great thing to add. I would love it if we could handle the PyData sparse library, sparse formats of sparse arrays. That is actually a great question. Thanks, Anthony. UMAP for outlier detection. I mentioned clustering earlier. It is notable that UMAP has a tendency to pull everything into clusters in a way that's very nice, unless you're looking for outlying points. So the new release is going to add some extra parameters that you can add on. Unfortunately, currently, still not especially well named. This is based on the background mathematics involved. Set alt mix ratio, but the point is you can set this and the end result is that it produces an embedding that is probably not the embedding you want for visualization, but it retains outliers as more outlierly points. And thus, if your goal with UMAP is to run an outlier detection algorithm, you can run it with this in mind and get pretty powerful outlier detection that's going to run a lot faster because you're running outlier detection on low dimensional data instead of very high dimensional data. And then just some fun ones. Embedding into non-Euclidean spaces. This is again work by Joseph Courtney, and the goal here is that UMAP embeds into a plane, a 2D plane, which is just a nice flat Euclidean space. But in principle, it can embed into any space you like. So we could say we want to have a sphere and embed the data onto a sphere. And the end result is we can have UMAP produce an embedding of the data on a sphere. So if your data actually has sort of interesting cyclic structure and you know that and you expect that, it's hard to embed that in a flat plane. If you think about maps of the Earth, you know, you always have to tear the map, and Antarctica looks huge and Greenland looks weird because you're having to do a weird projection. If you know your data has that structure somewhere, you could embed into a space where you don't have to do that weird tearing. So this will allow you to do that. It's actually pretty powerful the way that Joseph got around to writing it. You can provide your own distance metric function for the low dimensional space you want to embed to. So here we're writing a custom distance function on a torus, and now we can embed data onto a torus.
Cool.
Now, toruses and spheres are neat, but maybe you want something a little more practical. We've added an option for an output metric of Gaussian energy. So what this is doing is embedding the points embedding the data not as points in a 2D space, but as actual Gaussian blobs with covariant structure in that space, and measuring the distance between the actual Gaussians under a Gaussian energy distance model. So what this means is that each point has a location in the space that it's embedded to, but it also has a covariant structure of sort of an uncertainty of where that embedding goes. So for example, this point here is actually pretty uncertain about exactly where it's going to go, whereas a lot of these points here, they're pretty confident about where they're going to land. So you can end up building out nice density maps of where your data is landing based on that. So this is actually a pretty powerful feature. There's a lot of interesting ways this could probably get used that haven't been explored yet. So this is another potential way to contribute, would be to think of interesting ways to make use of this sort of ability to do more interesting things. I think I have hyperbolic space embeddings, if you like Poincare disk models in your mathematician, as a fun extra. So that's what's upcoming in the 0.4 release, as far as I know at the moment. But there's further stuff. So upcoming is the start. Sorry, go ahead, Anthony.
Oh no, go finish off. Sorry. Yeah.
Upcoming is the start of multi-core support. So this is some great work by Tom White, who went in and did a fantastic job of making a parallel version of the nearest neighbor search. And in fact, that's all getting factored out now into its own separate library for nearest neighbor search called PyNN Descent, that pretty much took the nearest neighbor search from UMAP, made a library of just that. And in the end, that's going to be a dependency for UMAP. UMAP's going to have all the nearest neighbor search code ripped out, and everything's going to be added to the PyNN descent. But Tom also added some code that makes it potentially possible to do multi-core support for the optimization step as well. So this is still in development, but there's good hope that we can have actually a multi-core UMAP running in the not too distant future. And if people would like to, at the very least, check out some of the development versions and play with this and see if it works for them, I'd love to hear more about how that's going.
Sounds like a great idea.
That's amazing. Well, we have a ton of questions from the users today. So
that's an amazing thing. Wow.
Yeah, it's really great. So just to reiterate one more time, these are all places that you can jump into the UMAP project or the PyNN descent or any of the dependencies and really help out either with code contributions or with funding if that's something that you're interested in. And we're really excited to see all the places that UMAP is going in the future. So with that, we're going to get to our first user question by Jose, who asks, is UMAP primarily for visualization, or can it also be used for clustering? I feel like you answered this kind of, but I'll let you take it.
Yeah, so I think this is a question that comes up because there's a belief that t-SNE is really just a visualization tool and you shouldn't use it for clustering. And I could go either way on that. I think you can use t-SNE for clustering if you're very careful about it. But I think with UMAP, it specifically has features designed in to help you do clustering, and there are ways to tweak the parameters to try and ensure the clustering works better. You don't have to embed to only 2 dimensions. You can embed to 10 dimensions, which I think t-SNE would struggle with, and do clustering there. That gives you a lot more flexibility in doing your clustering. So I personally have used UMAP to do clustering quite a lot, very successfully.
Great. Good to know. Okay, another question from Krishna. I suppose the more precise way to phrase the question is, what is the basis and probability for UMAP? So if you have C different groups, then probability that observation Y belongs to group C_I, so probably Y in C_I of X.
You know what? I am not a probabilist, so this is the part where normally I punt to my colleagues at the institute who actually know statistics. I'm actually a topologist,
so a question
yeah.
in issues or something like that, right?
Yeah. If you submit an issue with those sorts of questions, then I or some of the other collaborators or my colleagues can hopefully provide a good answer for that. I don't have one.
That sounds like a good place for questions in the docs kind of section.
Yeah, totally.
To cover the conversation in as much detail as can be. So our next question comes from Sun. How do we interpret the distance in the plot? I believe this was referring to the UMAP plot and the distances between the clusters and the points. So,
yeah, so this is a little bit of a tricky question because I think people would like to be able to fully interpret the plot as distances are meaningful globally. UMAP is similar to t-SNE in that it focuses mostly on getting local distances correct. It does a better job, in my opinion, than t-SNE of getting the sort of longer scale distances between clusters and relationships between clusters more correct, but it's not getting them 100% correct. So my general belief based on how the theory goes through is that it's perfectly okay to do qualitative comparisons of measurements. Like if there's visually a clear difference, these clusters are really close together and this one's far away, that's a statement you can make. If you're actually measuring distances on your screen, that probably is not the way to go. So exact distance measurements in the low dimensional space are not going to be 100% meaningful, but the qualitative distance measurements are generally meaningful.
Okay, makes sense. So this question is more a did you know or have you heard of? Sonu had asked, have you heard of the Streamlit library? And the comment about it is it may make plotting faster and easier.
I have not heard of it. If Sonu would like to submit an issue, I would love to find out more about that. And if he has experience with Streamlit, if he'd like to submit a pull request, I would love to have that as well.
Sounds like a great way to take care of it.
Yep, sounds like an amazing way to get involved. So Raphael asks, what does it mean to color by the current estimation of a dimension at a given point? This was suggested as a way of coloring.
Right, that was in the diagnostics plotting options. So the goal there is that you can get an estimate of the local dimension at a point. Essentially, what you are going to be looking at is looking at the local neighborhood of a point in the high dimensional space, and then assuming that things are locally linear, you can use PCA and see how many dimensions you need to get up to a reasonable amount of variance explained in the data. And that varies point by point across the data set. And this gives you an estimate of sort of the local dimension around that point. How many dimensions do I need to sort of explain the data local to that point? So that's essentially what that's doing, is it's providing an estimate of what it thinks the actual dimension in high dimensional space actually is local to that point in terms of the data. Hopefully that answers his question in a way that he's
well, if not, he can ask it in the issue, right? So Jose also had a question of, are there statistical properties that are being preserved in the dimensionality reduction?
So sadly, I'm going to punt again as a non-statistician. There are topological properties that are preserved, and I can certainly speak to those. It's really attempting to preserve homotopy equivalence between the topological representations, and that it does do. But as to statistical properties, I'm not a statistician to be able to answer that. There is a master's thesis that someone published on simplicial autoencoders. So if you Google the term simplicial autoencoders, I think you'll quickly come across the thesis. And they actually did some statistical analysis of UMAP, which I didn't entirely follow as a non-statistician. But if you want statistical answers, that might be a good place to start looking, because it's somebody with a statistics background who dug into this a little bit more.
New, I am not a lawyer. I'm not a statistician. So Sun asks, in single cell biology, where each cell data point is presented in several thousands dimensions, genes, people usually perform PCA first and then use the results from PCA to do UMAP. Can you comment on that? Probably on the effect of the combination of, basically just comment on PCA and UMAP together.
Yeah, so this is an interesting one, because I actually believe that that's definitely not necessary for UMAP. t-SNE, because of the way it works, it actually really needs your dimensionality, ambient dimensionality that you're starting with, to be in the sort of 10 to 100 range, ideally. It doesn't work as well as you get up to higher and higher dimensions in terms of how qualitatively well it does a dimension reduction. And UMAP has some tweaks to it that make quite a difference. Mostly it has concerns about local connectivity of the manifold, and that means it handles really high dimensional data surprisingly well. And so my belief is that you really don't need to do that PCA step, especially because UMAP can handle natively sparse matrix format data you can hand it the thousands and thousands of dimensions directly, and UMAP can just operate straight on that.
Cool. I think we have time for a couple more questions. Krishna, this is sort of a workflow question. One challenge with UMAP, I remember, is choosing the number of clusters beforehand. I believe the user has to specify the number of clusters, and then UMAP proceeds from there. If I don't know the number of clusters up front, is there a way to try 2, 3, 4, 5 clusters and get a goodness fit metrics on all of them? Or is there a way for UMAP to find the optimal number of clusters?
So I'm going to presume he means embedding dimension. UMAP doesn't actually produce clusters by itself. So if you're talking about what dimension to embed to, 2, 3, 4, 5, and so on, you can certainly run some goodness metrics on that. How well you preserve local neighborhoods is a pretty standard one. That was in the plotting library. That's not a function we have in UMAP natively, not least because it's not a great metric. It's just one of the few that measure anything useful. If somebody would like to add it, we could certainly have it in the library, and then you can look at how that changes as you vary the local dimension. And that would be, sorry, an embedding dimension. That would be a reasonable way to go about doing that. One of my colleagues actually went through that process to try and work out what the best embedding dimension for a data set he was working with was, and it ended up with between 9 and 10, which seemed a surprising and odd answer, but he tried everything from about 2 up to 25, and 9 or 10 seemed to do the best job.
I think we're out of time now for questions, but we had a couple stray questions, so if you still have them, feel free to file an issue with them, and I will take the action item for Leland. If you answer them, I will document them. And with that, I think, Anthony, it's our rant section, isn't it?
Yeah, it is now time for our world famous rant section, where we each get 15 seconds to rant or rave about whatever topic we want. Leland, it is your soapbox.
So I want to rant about number. I believe that number is actually the future of performance numerical Python. Python is going to go away eventually. Number might not be there yet for the big projects, but I really believe anybody who's using Python right now should be at the very least making a long-term migration plan from Python to number, because number is going to be the future.
Well, that's certainly a rant or a rave. I'm not sure which one. So my rant is just very simply, there are so many keyboard shortcuts. Why, oh, why are there so many combinations for all these different applications, and who can possibly remember them all?
Yeah.
And Anthony, it's up for you now.
So my rave for today is that I want to express my gratitude for the many projects I work on that have a bus factor of much greater than 1. It's really nice to be able to step away from things from time to time. And that is all the time that we have for today. Thanks for watching. Thanks for listening. You can find us on Twitter at Quansight AI. If you're interested in funding open source projects, including UMAP, you can find all of the project roadmaps at quansight.com/projects. Leland, where can people find you and UMAP?
So there's the UMAP GitHub page is available. Hopefully that's going to be posted to the chat. It's github.com /McInnes UMAP. If you Google, you'll find the docs pretty quickly, but umap-learn.readthedocs.io, and you can reach me at leland.mckinnis@gmail.com.
Well, thank you so much for joining us today, and be sure to tune in next time for a discussion that is guaranteed to have great returns on Econ Arc. Thank you, everybody.
Thanks, everybody. Thanks, Leland. Thanks, everybody.